That's
Mhm.
so okay. Let's start our recording, and yeah, I think we can do some warm up as always to like talk about definition of functions. You want
Yeah.
to start? It doesn't matter. Just we can just doing warm up. So
Um,
I mean, it is warming up here, but
you mean like just functions in
yeah,
general?
definition of function.
Okay,
I-
so if we want to define functions formally, we can say a function f from a set A to another set B is a subset of the like Cartesian product relations, where actually follow some specific rules. Like for every element in A, there are always a unique element in B, and it never actually matches to no single element from A matches to two elements in B. Uh,
Mhm.
yeah.
Want to
No, no,
exercise?
no, no additions so far, I would say. That roughly is
Okay,
what I guess.
let's mix them like okay. So let's try the definition of no, injective function. I'll take subjective. So what's the definition? Injective
Yeah,
or
yeah.
one-to-one function?
Uh,
Yeah.
i-
Mhm.
if the value of the two values of the function are equal, then they must have come from the same element, essentially. So if f of x1 and f of x2 is equal, then x1 and x2 is equal. I would say that.
Mhm.
Yeah.
Okay. So I would say definition of surjective function. So onto functions, which is also surjective function is so it's a function that every element in codomain is mapped from elements in domain, which means image of f is equal to codomain of f, right?
Yeah.
Yeah,
Yeah.
yeah. Okay. Okay, so I mean it is elementary, but yeah, so it's good start for like waking our brain up in Monday 8 a.m. in our case.
Yeah. Yeah.
So last week we covered the second note from like some images, and also we have composition, especially we have some exercises to show one-to-one function is if and only if there exists a left inverse, and the onto function exists if and only if there exists a right inverse function. And that there was like exercises. So I think we can quickly review what we have done, and I think we can dive into our exercises about like left inverse and right inverse in terms of the like yeah make the composition identity. So any supplementary comment for like inverse images?
No,
No.
not so far actually.
No.
We have discussed this in length.
Yeah, yeah. So I think we have now we have some clear like picture about inverse image. Okay. So let's revisit our definition about one-to-one and onto. So I think composition comes first, or
Yeah, let's
yeah,
take a look.
here we have injective and subjective. So like in our course, we express the injective and surjective as in terms of the codomain,
Mhm.
I mean image. So every image has one. at most one pre-image we call that injective, and every image has if every image has one at least one
Pre-image.
pre-image, we call that surjective. And in this case, I think it has more maybe practical. So it means the image is same than the like its pre-image should be also same. So different expression, but yeah,
Same idea.
same
Yep.
idea.
Mhm.
And I think this way is more useful, especially when we deal with some proof. So we want to argue in like formal expression, like using why is it always okay? Like this statement is I think useful, or I mean it is most commonly used when we show something is injective, right, Tanfi? I mean, as your experience.
I mean, this form of definition is the most
Yeah,
common.
yeah.
Mhm.
Like
Yeah, exactly.
yeah, default. So even what I remember is even we define the injective as like what we just said, like every element in codomain has at least one, I mean at most one pre-image. So it would map, it would have zero map or just one map. But even we define like injective that fashion in our linear algebra course. But I found that even in the lecture we are using this argument in our proof. So
Mhm.
I think it is always also useful if we have this argument in my mind, if we want to show something is injective. Yeah, that was maybe my comments.
Maybe additional, we can just say that for injective case, we can have in the image some unmapped elements possibly. But if we have some mapped element, then it only comes from a single value, not from multiple values. So just
Yeah,
the way to
so
rephrase it. Yeah.
so you have think of it as if it has so if it is mapped, it should be just
From one.
from one,
Yep.
or it is just not be mapped.
Mhm.
So like you divided like these two different types of like elements in coterie. Okay, I think
We can
that's
have
also
the same drawing probably for surjective. Then we would have, we can say that every single element in the domain, so the image essentially, every element has to be mapped. So the image actually covers the full domain, so domain and image correspond to each other exactly, and then we can have then multiple source, multiple pre-image elements mapped to the image single image element. But then every element in the domain is covered, so that would be a big visual difference essentially on the diagram.
Okay. And also like so in surjective we call like image is equal to codomain. We use this argument, right? And I think like the way we argue with image is equal to its codomain. I think sometimes we use like we argue with comparing dimensions sometimes, right? I mean, so like what I remember in our linear algebra was image of F is subset of B, but dimension of, I mean, we only like what in dimension in this case we only do have we had experience only in finite dimension, but dimension of and dimension of image of F is equal to its codomain, in this case dimensional B. Then we can conclude, image of F is equal to B, and we get F's surjective. So what I remember in our linear algebra was like yeah, argue with dimension if we have like maybe, yeah. Comments from Tanfi?
You are writing dimension of image of f equal to dimension of b. And then you wrote image of f equal to b, so f is surjective. So this is more of a like if dimension of image of f equal to dimension of b. So then
Mm-hmm.
we will get a surjective function.
Mm-hmm.
Yeah, yeah. So it makes sense then. I mean,
Mhm.
it's not necessarily always, just when it happens.
Mm-hmm. Yeah. Maybe wrong brackets here.
Oh, yeah. Mhm.
Mm-hmm. And there's another expression that for any y in B, there exists A in A such that FA equals to B. It also reflects our expression of like every element should be mapped,
So
right?
basically, I think it means that no unmapped elements can exist in case of a surjective function.
Mm-hmm. Mm-hmm. Okay, I think we can go further.
Mhm. The bijective is just a combination.
Yeah, bijective is just combination,
And in terms of the definition we had, so at most one and at least one, and then when it's both at least one and at most one, it's exactly one. So one-to-one mapping is what we want in bijective case.
Mm-hmm. So another comment. So only in bijective case we can define a inverse function, right?
Mhm. Well,
But
the full inverse function, right? Because we can have the left inverse function and right inverse function.
yeah. I mean, yeah, the proper inverse function.
And I think also we can say, like, for example, in calculus, we have the left limit and the right limit, and if they're equal, then we have a limit for at a specific point. And then in here, if we have the left inverse and the right inverse, we then have an inverse function, and therefore it's bijective as well, right?
Mhm. So yeah, so in this case, inverse function is really strict that it really needs the same. It really also have to switch the domain and codomain. Not only like,
Mhm.
but if we just give up the domain and codomain, I think we can also maybe like represent the map in the other side. We can find the function. I think we will argue with that in our exercises in like left inverse and right inverse. Yeah, but let's see. And yeah, another one was about, so we also deal with this like expression which we can um, express it as a pair because we define the function as a Cartesian product, subset of Cartesian products. So yeah, it is also have for me, I think it was useful. I think you're flow. Okay.
No.
For me, I think it was also useful to get both perspective, like like which looks like this.
Mhm.
So in my mind, as a picture, I have this like arrow mapped as a function, but in other side, I have a picture of like this pairs, set of pairs, which is so to speak data type
I
of
think
function.
generally we shouldn't really tie ourselves to different representations,
Mm.
but just know that they're interchangeable, and that's exactly what we want in math. I think we want to preserve various properties, and how we show it should matter secondarily to what we want to present as a concept.
Mhm. Okay, and in here we define the composition here. Yeah. So it is also so actually in function like until school days I really does not care about the domain and codomain. Like I didn't even care about like what are they because I think in school days it was more focused on like really just do how the function was like expressed, how the maps looks like, and maybe the domain and codomain was almost in real function. And also maybe in like trigonometry functions, we have like certain like we have some
You mean
restrictions in domain, but I think I really haven't thought about like domain and codomain as a concept. But like from this stage, it is really also like required to think about the domain and codomain, right?
Yeah, but again, I think maybe in school the main idea is that you can perform the calculation and do some basic analysis with what you are given. Whereas in like university math, you generally would want to generalize various aspects and figure out how to think in general about any types of function and be able to compare them without going into a specific calculation detail.
And like from the first time, like so another like maybe side comment about the um composition was like we actually learned this composition from the very beginning of the our course, right? Even the very beginning of our first semester.
Mhm.
So okay, so what's the big deal about composition? Like it's just composition. That's what I thought. But like the further I learning like concept, composition is really important. Like one example comes to my mind is like normal operator in linear algebra. We have endomorphisms, and if I'm not sure. I- Is it? So is this definition of
You
normal?
can in this case like the commutativity, right, of the elements essentially of what they or like you can think of operations as being the elements with which you do something. So composition would be the commutativity of the operations
Mm-hmm.
as well.
Oh, what you mean?
So here you combine first you apply first F, then you apply G, or you first apply G, then you apply F, and this order matters.
Yeah,
And this
order
can be
matters.
considered like commutativity. Usually you would think in terms of swapping the elements while the operation is left intact.
No, I mean it is not commutative, isn't it?
So basically when you have a bijective function, can you say that the forward function and the inverse function are basically commutative in this case for a bijective function? Would you be able to say that?
Mhm.
I don't think it's expressed in those terms, but can you sort of think of it this way?
I mean, even if it is bijective, it should also have like
So basically, when it is bijective, we know the mapping is one-to-one. So all elements of the domain are mapped uniquely to all elements in the codomain, which means that you can go both ways and you end up with the same result. And it doesn't matter whether you start in the forward way and then invert it, or from the inverse way and then go forward, you will end up with the same, well,
so. I think bijective itself is not enough for like sufficient for commutative in my case. So if we have like function f mapped to 1, 2, 3 to like a b c,
okay.
and g to like a b c to like something like
Also 1, 2, 3, or?
no 4, 5, 6.
You mean the general composition, case of general composition, not the composition between when we have the inverse domains, essentially domain and codomain. So F would have the inverse domain and codomain as the G. So I'm thinking if A is from A to B and G is from B to A, then we would have that. But if we have F from A to B and G from B to C,
Yeah, so
then we yeah,
in this case, even they're like bijective, but let's say this is a b,
yeah,
b, c. So
in this yeah.
yeah, so bijective itself is not sufficient, but also their domain and codomain also should be switched.
I was thinking about its bijective and also its function and its inverse function that we're talking about.
Bijective and
And
it,
F
it,
and
it
F
and
minus one.
yeah, yeah,
Then in this case, I think we can.
yeah. I think it's always. What was the question?
Just can you think of it as the commutative? So you can change the order of F and F minus one. And basically you
No,
can, well, you basically get this different result. You go from either
yeah.
1 to 1 or you go from A to A in the end with the combination. So
So
it's not exactly,
yeah,
not
yeah. So
exactly
it
like
is.
that, but it just the idea of order of composition of functions plays a role
Yeah,
generally.
plays a role.
Yeah.
Oh yeah. Also, like we can think about like if we have two matrices, both of and the multiplication of those matrices is basically a composite function like A B.
Mhm.
Mm-hmm.
So technically, even if A and B both have inverses, AB is not equal to BA in general.
Mhm.
So that can be another example, like what Philip just said, like the composition or commutativity.
Mm-hmm.
Mhm. Mhm.
Yeah. So yeah. So in that sense, composition functions plays some vital role in the linear maps when we try to just combine them, like A and B and AB, whatever. As every matrix actually represents a linear map, right?
Mm-hmm.
Okay, I'm not sure whether it made sense. Okay,
Yeah,
let's move
yeah,
on.
I think that makes it because we also like we also always like um have two sides when we doing like linear algebra. We take linear operators and we also always think about it in metric size and compare. So like
Mhm.
in linear like composition in linear operator is also equal to like multiplication of matrices because
Mhm.
yeah. So in matrix multiplication is generally associative but not like
Commutative. Yeah.
commutative,
Yeah.
yeah,
Mhm.
generally. So I think it also mm, yeah.
Yeah, and also I'm not sure, can we generally discuss that linear operators and matrix operations in terms of equivalence classes? So would we say that
Mhm.
they're, because we can do both and
Yeah, yeah,
convert
they're
between them
like
directly?
isomorphisms,
Yeah.
yeah. But mhm. Yeah, I think this is also good perspective to think about it. And yeah, but I think in this case we can't in this case we can't really think about it as a matrix multiplication because like like B is not even a field, so I mean B is not a vector space, so we can't think it as a like linear operator. Or can we?
No, it's just the it's just the rule we apply how A like elements of A goes to B, right? The matrix represents that.
Hmm.
So B we are not actually dealing with B here. The matrix itself is just the rule where actually the mapping is happening. So this F will have an associated matrix. This F inverse will have an associated matrix. That's what I'm trying to say.
Mm-hmm.
Like maybe let's just say f is a function from a to b. For every x in a it will go to ax which is in b. So x is a vector in this case, although we are not dealing with vectors. Let's just say that.
Really? Hmm.
And in this case every one and a or two or b or whatever it is just some objects. We are not even saying what does two mean here, right?
Hmm.
Yeah, I think it's actually the mapping that plays a role, so not the object itself with which you're dealing, and then you can, it can either be a vector or it can be a scalar value. And
Mm. Okay, I'm not sure because like my concept is like restricted under like linear operators and
Mhm.
their like transformation matrices, which is like isomorphic
But
with each
I think
other.
basically when we're talking about linear operators, we're talking about vector spaces, right?
Yeah.
And the vector spaces assume that the objects within the vector space are vectors.
Hmm.
So I think that's because of the type of object that we're dealing with, because of the type of mapping that we're talking about.
Okay, so this is a bit like side note, so I think I will keep it and
Yeah.
keep it and think about it. Like, but I think it's our privilege because we are only like 3 years, so maybe we can talk about some side things. But I think okay, I think now we can get back to our points and okay, where were we?
We were talking about generally function composition, so we're in the
Yeah, function composition. But like associativity is always hold in composition, right?
I at least I cannot see why it would not hold.
Yeah, I mean, I I remember the like results. The associativity is holds in composition,
Yeah,
and
I would say yeah, but basically for to check it, we would need at least three functions, right?
Mhm.
Because we will need to see one order of execution and another order of execution and see if it's the same. It gives the same result essentially.
So this is equal to
Yeah.
proof exercise. Okay, I think about it, but like.
Well, as long as this is well defined the composition, like every composition here, so we can just take elements, like we can take an element of hx, so we'll see that this goes somewhere in f, which is basically somewhere in g, and it happens the same in the right side also.
Mhm.
Like we can take h of x, so it's basically g of f of h of x, so then basically it's again just something in g.
Mhm.
Yeah, associativity is more of like so general in a lot of cases, almost. I guess in every mathematical structure they are trying to define, almost
Mhm.
always the operators are associative.
Mhm. Okay, so I will keep it also.
Mhm. Maybe we will come to that at a later stage when we give like as an basically yeah we have to figure out. So we are trying to cover some material and cover the basics more thoroughly, and then later on we can explore more specific cases or more longer cases essentially with what can be done with it. I think.
Mhm. So yeah, also as usually like composition is also expressed in
Pairs
like
and
pairs.
mhm.
And so we have our exercise here. It's about like injective if and only there exists a like function.
I was just thinking maybe when we see it expressed in pairs, how do we express composition in terms of like the sets and subsets when we're talking about three or more functions? So how would we show that in here?
Like what you mean,
So
like three of
composition of g of f of h would essentially be a pair from a value x to g of f of h. So it will still be one pair.
Yeah,
We don't
yeah,
need to consider triples
yeah,
or
yeah,
other objects, right?
yeah. I mean, even like so like now we are starting like multivariable calculuses. So
Mhm.
we have our domain now like this.
Mhm.
But even in this case, it's just two pair, like tuple of tuples, right?
Mhm.
So it looks like multiple inputs and multiple outputs, but actually the multiple is as a tuple and output is as a tuple. There's just only one pair,
Mhm.
which like,
So a
so
pair is a single element essentially.
yeah. So I think like really stick on the definition of function, which is Cartesian product of two
Mhm.
like domains and codomain is really important to like not lose in like maybe some tricky situations for me.
Mhm.
So we have like that should be a like
But then here we
and
have, for example, Rm is essentially R times R times R, like Cartesian product times R
mm-hmm,
m times.
mm-hmm.
then you would also think that in here the domain would be composed of Cartesian product tuple, and the codomain would also be Cartesian product tuple.
So it was, another side note. I don't know
Yeah,
why
yeah.
today
No, no,
we have
just
a lot of side notes,
yeah, yeah.
but
Uh,
yeah, but yeah, okay, but for me, I always try to, as I already said, like think of like in two perspective, like as a pair and as a like mapping. And yeah, so finally we start, encounter our exercise about, um, so in this case we have injective and surjective, like one-to-one or on-to, maybe more like US friendly. Um, so in this case, also we want to think about the like function g in each case, which makes the composition will give an identity. So in injective case, we have left inverse. We can find a g as a like left composition to make that identity. The composition
So
as an
we
identity.
first we go towards the image and then from image towards the pre-image value, right? The order is that. So we go from F to G and from G back to F.
So I suggest we can I will draw some like mappings in our right hand side, and maybe we can think about the situation. I mean, why in the injective case it is not allowed it to find the right inverse, and in onto case vice versa.
So again, with the injective case, we can have in the codomain some unmapped elements, and we can see from that. So just draw one part. So like in the domain, we have all elements mapped, and in the codomain, some are unmapped. And then when we go, and then before here, maybe.
So we will think about G. So
And by the way, here, do you then call that a left inverse, right? Or that's how you call it, the left one. For the injective case, you call it the
yeah,
left
left
inverse.
inverse.
I'm just thinking, why is it called left and the other one is right?
Uh,
So which way is left, which way is right?
yeah. Sorry. So I think it is like literally depends on the physical position in the composition, right? That's how I am like deal with this left and right.
So essentially here you would say right is the your codomain, and you go from the codomain back to the domain, and that would be left. Is that the left, the direction in which you go? Or
So it means like F comes first. We think about map F 1st, and then we will deal with tree. So that is like left inverse.
Yeah, no, I'm just
Yeah,
the word left itself. Well, it comes from the idea of how it's represented, or
maybe I will tilt a bit because I'm always in the right side of these tablets. So can I just copy this? Okay. I'm a bit lazy, so oh no. I think maybe it is not even more faster than I just wrote down, but yeah. So let's think about so this is actually left inverse case, right? Like left composition of G, and we have to make this whole mapping should be identity. This is our like situation. I'll say IDA because we want
Can we think that G is applied from the left in this case? That's why it's left inverse? Because you can say that G is applied from the left or G is applied from the right when we're talking about.
You can just.
No, I'm just saying that because where G in here is applied from the left, that's why we call it the left inverse, and if it's applied from the right, that's why it's called the right inverse in this case.
That's how I just accept it. Like, do you have some different opinion in Tamfi?
No, actually. So we are just trying to match the domain basically. So in this case, the right inverse will not make sense even, right? Like g of f, we cannot just say f of g because the domain will not make sense. So
Yeah. So in this case, like it looks like simple because like I think we can even use like this because
Yeah.
I think it would be okay. So it looks simple because like we can just map. We want identity of A, so map B1 to A1 and like B2 to A2 and B3 to A3.
So
The problem is,
maybe here it will be easy to show, okay, we have seen visually that it is surjective, but if we inverse the order, so we go from first from B to A, then from A to B, then we would not have, so basically it's not surjective. Maybe we can show with this diagram that it's not surjective. So we have shown here visually that it is injective, right?
Yeah, but I mean our G is still not like defined because we to like G is this map which has like B as a domain. It means we have to map every element in B, and we does not have
yeah,
B.
basically it's not even possible because we cannot map the full domain back to A.
But it is possible if we just map B4 to like any element.
So either we create an additional mapping
Yeah.
or we say we cannot do it, right?
So what we want to do is just find the function g, and it does not means g is also have to be injective. We have like f is injective, maybe 1 to 1, and we want to find some function g that makes f g composition f as identity.
So with G currently here with the red line, so with an additional mapping, it's still okay. It's still, the function f is still injective, right?
F is injective,
Even though G is not
injective.
Yeah.
And even G is not unique, right? Because we like this is like let's say G3 which maps to A3 and G2 which maps to B4 to A2. Oops. And so on. So in this case, we have like 3 versions of G that can make G composition F to identity, right?
Yeah.
So maybe this is like ideal situation, but I also want to visualize why we in injective case why we can't have like right inverse. So this was a left inverse, which means G composition F is identity of A, where F is 1 to 1. So I suggest we also take a look at what happens, why we can't F is why we can't when F is 1 to 1 and like right inverse of F. Yeah. We can't it does not have right inverse means we can't find G like that, right? I suggest we try and take a look what happened. Like I want us to get a picture and like.
So again, we are applying, if we are applying G first, then we have to cover all elements with the domain B, right? So we start in B. When we apply G first, we start in domain B. And that means we have book B1, 2, and 3, and 4. So all of them have to be mapped.
Mhm. So in this case, it means like, yeah, then it, even like we want identity B, which means like B to B
Mhm.
maps like itself, but it is not even possible from here because
Yeah, and even in the case specifically that you drawn, you can see that in A there are only three elements. So A is actually smaller. So basically you lose information immediately.
yeah. So there's no way if F is like injective
Mhm.
or one-to-one, there's no way to cover like more than the maybe so-called dimension of the domain when we have like unmet in our codomain.
I was thinking basically if you can imagine, so can I
Yeah,
phrase
yeah,
that?
yeah.
So let's say we map it almost exactly like that, and just one of the elements is mapped. Basically, you can say B3 and B4 are both mapped to A3. The problem is, okay, if we could alternatively consider, we can say, okay, let's choose just one of the directions in which can go. So it has two paths in here, but let's just choose one of them, right? But then it essentially means we have to make a choice, and this making of choice is a bit weird. And I would, so yeah, basically we would have to choose either we go this way or we go this way. And I'm just wondering if, because you mentioned there was an axiom of choice,
Yeah.
is that about roughly this selection
Maybe,
or something else?
yeah. So in surjective case, I think we have to consider about that. Yeah.
Mhm.
But yeah, so but I think that feeling is exactly right. As I maybe I have same feeling about that, but I'm not exactly know what axiom of choice is. So maybe
Shall we
Tanfi could.
look up? Did you encounter it in your studies?
Yeah, briefly, not in detail actually. I
Mhm.
mean, it's mostly like uh, not a thing to discuss with professors, but we have studied as a formal statement. Let's just say that.
Yeah. So like axiom of choice is like also some like sort of like set theory or like maybe in some axiomatic system.
Yeah, it's more of a like as we have studied, like if you have a collection of non-empty sets, you can pick one element from each set, even if there are infinitely many sets and no rule for choosing. So this is the informal thing we have learned. So of course there is a formal definition. We can discuss
Mhm.
about it later.
Mhm.
And here, okay, so we are discussing here that like why we cannot compose G after F, and it is not going to give us the identity of B as uh, are you somehow suggesting here that even if we define G first, but we cannot define F again after that as F is one to one? I mean, it is not going to give us all of B again.
Mhm.
Yeah, yeah, makes sense. So it's basically like if F is one to one, but G is not, so we cannot get even identity of B.
Mhm. Okay,
Okay.
so thank you for your comment, and I think we have seen enough about like injective case.
Yeah,
One more case, maybe we
basically
can go
when we go
further.
to the surjective one, we'll also be able to do the same thing and
Mhm.
show the order. So in one way it goes well,
Mhm.
but in the other one it doesn't.
Mhm. So so it has problem about this cannot be met, and it means there's no right inverse, like no such function G that makes F composition G as an identity.
Mhm.
So let's think about on two case. I also use notation F, but in this case, okay. And so maybe let's think about in this case
And then from the definition again for the surjective case, we say that it is surjective if and only if there exists a G such that F after G is the identity of B. Is the identity of B.
Yeah, but identity of B?
Yeah, that's the one.
Yeah, makes sense because we apply G first, so I think I always have to tilt this a bit. So let's think about as it suggests, let's think about the right composition. So our goal is to make this composition, sorry, composition as identity.
So we'll go
So
from B to A and from A to B, and then let's try it out essentially.
You mean 1 to A?
Yeah, 1 goes to A, 2 goes to B, 3 goes to C.
Yeah, so 1 goes to A, 2 goes to B, 3 goes to C. So in this case, we have, yeah.
So it looks like it's totally fine because we can still invert, because we started with fewer elements in this case, we can still return to those same elements.
But
yeah, the difficulty will come when we go to A in this case because it has 4 elements, and then in the opposite direction we won't be able to perform the same thing, right?
And in this case, it is also not unique, right? Because we can also think about
So we're talking the G is surjective, right?
G is surjective.
We're
F is
talking that F has to be surjective.
G can be any function.
Actually, my question is, can G be surjective as well?
Can G?
Yeah, can G be surjective?
So if we think about like, so let's not think about bijective case.
Okay.
So if we have like surjective case, subtract bijective case without bijective case, then it means like the domain of F is larger, like let's say larger.
So for G to be surjective, it has to cover every element in the codomain. So it has to map at least one of the elements to multiple. So we cannot do that, right?
Yeah, only F is bijective we can make G also surjective, which is bijective.
So can we have a surjective function when the domain is smaller than the codomain? So can we make a G here be surjective?
So
Will that even be a function? I mean, if
Yeah,
the domain is smaller than the codomain.
it cannot be a function in this case, right? It cannot be a function in this case, right?
Why?
Well, if we try to map, since we need to map for surjective function, we need to map all elements of A need to be mapped.
You mean
and we will need
yeah.
in at least one element will not be mapped uniquely, and in this case, it will not be a function.
In terms of surjective, right?
Yeah, so we cannot even make G surjective here.
Yeah, that's right, I think. So in this case, we also have like not unique because let's say G C and G D both makes like F inverse G as identity. And so the notes said in this case we need like axiom of choice, right? Yeah, I think it was in this context because we had to
So the axiom of choice is about this GC and GD choice. Is that how you?
So axiom of choice like occurs in this thinking of mapping of three.
Mhm.
But for my case, in this like situation looks really similar when we have injective case. We also need to make B4 as mapping for like A1 or A2 or A3, right?
Mhm. But in that case, B was surjective and it was okay. Whereas in here we cannot make B surjective.
What do you mean?
So in the
B
pre
surjective?
in the previous
Like
case,
you mean G?
in the previous case, B was okay. Can I? I'm not sure where.
Yeah,
Yeah, this one. Yeah. So B in here was a bigger had a bigger domain essentially, and was as a function was surjective, mapped all elements inside of B to some element in A, and therefore because it was bigger, it had to map at least two elements. It had to map to the some same value in A.
Mhm.
But in the case, the second one for surjective case, B is smaller than A,
Mhm.
so it cannot be made surjective in such a case for G to go from B to A,
Mhm.
because you cannot reach every element in A because you have less elements in B.
Mhm. But what's the like relevant about axiom of choice? My question is, so like maybe in this case, in like maybe in this case we have to choose whether GC or GD, right?
Mhm.
And in this case also we have to choose like so I think it is not about this mapping. I think it's relevant about like choosing pick some elements in infinite elements of sets, like infinite sets.
Mhm.
So maybe in this case it does not require axiom of choice when we deal with like finite sets. I'm not sure. Maybe.
Yeah, I don't have a clear enough grasp of the axiom of choice. I think maybe again it will be a topic we might encounter later on in some more specific detail. But in here, I don't think we're well. At least I'm not clear enough on
Mhm.
what it does mean exactly.
Maybe should we
Find a formal definition or.
maybe I
Yeah, I actually this is a matter of thought, to be honest, because
do you
by definition, I mean, if you really think on the composition, G is defined in a way which goes from B to A. Okay, makes sense, and then Y goes to X. But according to the picture, we are not even like getting a function properly, right? Like if you really see the blue picture in the left side of your note, I mean the handwritten notes. I mean it's defined X and X dash which goes to Y. Okay, so this is our F, right?
Mhm.
Are you getting what I'm saying? So then if we want to define a G which goes from B to A, but technically this isn't even going to be a function or something, because we are actually sorry, this is going to be a function, but we are not recovering all of A, right? Are we? Are you on the same page as me? What I'm trying to say?
Um, So when we are going essentially in the order first, we go for G, so we go from B to A and then from A to B, everything is fine. But
Yes,
but when we are going in the opposite direction, we start with A, then essentially we cannot go back to A. Yeah, right.
yes,
So mhm.
yeah, yeah. Also, why the existence of such a G actually requires the axiom of choice is also something to think about. Uh, can't you just do it normally?
Uh,
Technically, if we want to define a function, we cannot do it normally because B has, let's say in this case, B has only one element, so it cannot go to two elements in A
mhm,
by
yeah.
default. one thing. And another fact is, even if we can define a function, we are not recovering all of it. Maybe only to x, or only x1, or only to x2, right? But not all of them. So what is our goal in here? Obviously not to define the function, I guess. We are trying to recover the complete A, right? Is that
Yeah,
our goal?
I would say, yeah, we try to recover the complete A, and in the
But
case where
in this
we
case, this is not possible, I guess.
uh,
But I don't know how axiom of choice actually gives us the opportunity to do that. But if it does, then well, it's more of a like, okay, defining two functions separately and then taking the union of the codomains or something, we are getting the complete A.
mm,
Okay, some thoughts.
Mhm.
mm.
Yeah, we have to actually talk about axiom of choice like completely formally. Then I think we can come back to this later.
Mhm. Maybe we can just think about, or maybe search about axiom of choice independently, and
Mhm,
maybe we can share our some thoughts in our channel with some comments. I
mhm.
think professor also like guide us, not so I think the point was not really deep dive on the axiom of choice, but just like let us know in this case we need axiom of choice. So I think it was like, yeah.
So
Yeah, but if you look at the structure, like uh, if I want to read it correctly, so that we can define g which goes from b to a such that y goes to x, and y goes to x makes sense. We are defining a valid function, but
mhm,
the existence of such a g requires the axiom of choice y. I mean, this should be natural. The g, I mean, we can define g easily. Y goes to x. Okay, fine, makes sense. But why do we need the axiom of choice in this case? Is it because like which elements of A we are going to choose or something? Okay, yeah, this is something to think about actually, maybe some other time.
yeah, maybe we just if we have for now generally for well next time will be a bit late, but I mean generally if we leave some read about axiom of choice a bit and maybe
Hmm.
leave some comments which help us clarify things, maybe it will be
Hmm. Yeah.
useful, right? Yeah.
Yeah,
So
yeah, yeah.
maybe like even in during like our break, we can share our thought and what we figure out in our like channel with comments, so we can like share
Yeah,
our
right.
thoughts. Like, okay, so it was like rights composition of F, which makes us identity of B. Is it or not? Sorry.
Yeah, the other way around. Yeah.
So let's also think about why we can't have left inverse or like insurjective or onto case. So let's have A. I think I have to tilt.
Yeah.
So in this case, this is not G. This is
So we're able to go with F from A to B, but with the G we cannot really go.
so it's also the same like problem because B is smaller than A,
Yeah.
so we can't even reach every element.
It would not be a function.
Yeah, G cannot be a function.
So I'm not sure. Maybe like technically you're allowed to have a mapping, but not a function.
Yeah, yeah. So let's say we can make a map, but it's not a function.
Hmm.
Okay. So it is quite clear, like after we visualize it, because like every time we have smaller domain than codomain, and we if we have to map every element, I mean, let's say smaller domain than image. I think that's more precise. So our image should be ABCD because we want identity of A. So every ABCD should be mapped, but we have smaller domain, so we can't make a function. Okay.
And maybe just one test case is that if A and B are equal size, so A has A, B, C, D, and B has 1, 2, 3, and 4, can we make a function so that goes forward and backward, so function and inverse function, such that it is surjective, but at the same time not bijective? So yeah,
So like in this case.
yeah, like in this
But
case.
this is
So
not
in
this is not surjective. This is just function, right?
So we want F to be surjective, but we want so basically the go to go forward and backward. Yeah. So essentially,
Well, if they have the same elements, then okay. If they have the same, I mean, same number of elements
yeah,
like A and B,
same number of elements. So
So
what my
that means bijective, right?
yeah.
then
So
they
what I'm
cannot be
saying, yeah,
surjective.
essentially because they have the same size, you cannot map different elements to the same elements in B simply because then you would not have yeah, surjective
Yeah.
coverage. And in this case, it will automatically be bijective.
Yeah, yes. This is the edge case of surjective.
Edge case of surjective.
And also even in injective. Yeah. This is even injective, so yeah.
But then essentially when we have one of them smaller, essentially when we have the B smaller, then we do have yeah.
So maybe I have also I get a view after this demonstration. I have a view of comparing the size of domain and its image. For example, like in injective case, we can think of like size of image is like I mean domain size of domain is larger. I mean it is not precise because but yeah. So in mapping, like yeah, I think I'm not ready to like think about this. Maybe I will clarify after like thinking about it.
So I guess any kind of comments that we come up with later on when we
Yeah, you can share in like our channel.
Yep. Okay.
Okay. I think it was great. Maybe should we take a look about equivalence relation and partition a bit? Maybe we can just read the note together and like
Yeah. If
maybe
we
we
just
will.
get the general coverage, we don't go into details. Maybe
Yeah,
like
yeah.
for now, just see the definitions.
Yeah,
Because we have around 15 minutes.
15, yeah,
Yeah.
15 minutes. And like after around like 10 minutes, we also maybe like think a bit about like after during our semester break, should we like change our like times or maybe after reading these notes? Okay. What I remember about like equivalence class and relation was like in our first semester, we also had like relations and its some properties like totality, reflexibility, symmetry, antisymmetry, and transitivity.
Yeah.
And like now I quit drink, but in first semester we drink some beer. We gather together and drinking some beers together, maybe eating pizzas and think about what can be like relation. Is it like reflexive, like maybe equivalence relation, I think. So we are thought about some various concepts, and one thing was maybe about like some kind of romantic relationship could be which kind of like property it holds. Like, is it like transitive?
Yeah.
It is like reflexive, like kind of, yeah. But I
I,
can't
I'm
remember
I'm
why.
gonna I'm gonna take this as a PR effect, by the way. But yeah.
Yeah, it was. I mean, yeah, we are still in recording, so maybe we can't speak like
Should stick to
really.
mathematics a bit more.
Yeah, stick a mathematics, but I think this maybe this was one good way to learn mathematics maybe get rid of the alcohol because the problem is I have a memory, but I really can't remember
Not the
what was
details.
the details.
Yeah.
Yeah. So that's a bit like, yeah, unfortunate point, but I think without alcohol, I think it could be a good maybe, you know, involvement to the concepts.
Yeah, yeah.
Yeah, okay. So let's go through together. So okay. So recall that function is a subset of Cartesian product. Mhm. And for each element, there exists unique map satisfying. I think this is what we always doing warm up in our session.
Just sort of a definition of a function, really, right?
Definition
Yeah.
of function. So it is actually a subset of Cartesian product that
Mhm.
hold two criteria. So every x in domain should be in pairs, and the pair should be unique. So x should not be like like it will appear two times. So until here, it was definition of functions, and yeah, so it says I think in here it is just like normal meaning of relation until now we are using, right?
Yeah.
So I think from now we will define relation as more precise way, and
That's just that basically we say that a function is a relation, but a relation is not necessarily a function. We just want to have it more clear. So the relation is a more general concept, right? And in here, I think we'll have some examples where we can see. Yeah.
So relation it is just a subset of a yeah given two sets. Relation is a subset of a Cartesian product B. Yeah.
I was thinking it was letter B. It was is a subset of.
The relation R is yeah. I
Is
also I
yeah. I was
it
thinking it
looks
was
like
B.
B.
Yeah,
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 B
yeah.
because it
Mm.
so yeah. R is a subset of a Cartesian B. So yeah. So as you said, like function is also a subset of relation. Then whole certain criteria.
And I think basically this symbol
Mm-hmm.
is used in equivalence relations because equivalence relations are special types of relations as well. So basically, but any relation is shown with this tilde symbol and R to indicate the one we're using currently.
So yeah. So so actually while I first in our first semester we studied like relations and equivalence relation and this tilde notation. So after studying that, every time I read some normal text, the like this tilde looks like always like relation. So
Relation.
I have some problem with like reading normal text anyway.
And also just to know that again, for a relation, we can also consider, like for a function, we can consider it as a set of pairs. But yeah, we will see that there is a difference, right?
So so actually we write down the pair as this relation notation. So in here we can find the like every pair we can write down as a like relation notation, right?
So can maybe a question, can a relation be such that it is a full Cartesian product of A and B? Is that still a relation? So it's definitely not a function, right? But is it a relation though?
Yeah.
Because what I'm saying is that here we have the symbol that it is a proper subset, but so it can be equal, right?
Yeah, but I think in this our like Kidesu notes we does not like really
There is no distinction in
distinct
those
for
okay.
my observation because like when we had like our power set the note said the definition of power set as subset of like this but in
Okay.
power set we have like a
Yeah,
itself too.
full, yeah,
So I think in this note we does not really
distinguish between those two
distinguish
symbols.
like
Yeah.
proper subset or just subsets. Okay. So I think we can go further. So it's a function. Let's say f a function, if and only if I think we need some context here because I think this SF means like subset of Cartesian product which fulfills the criteria of function, I think, I guess, because I remember the notation of SF when we define a function.
So it's like a set for a function.
Okay, so we have examples of students in college define. Oh, I think.
What does it mean?
Yeah, it's Korean. So A things B as a friend. It means like, yeah, A think B as a friend. So define this pair relation. So I think even my just short feeling about this introduce this notation means before this we have just like we just think about the pairs. But from here we really want to put meanings as a relation of two pairs.
So I'm just thinking that when we were talking about a function, we can say that one is mapped exactly to A, two is mapped exactly to B, and so on, if we do it like over elements. Whereas in here, we would say A is related to B, B is related to some other elements, and so on.
Okay, I think that is also one of the good points to think about the like relation notation and
Yeah, and by the way, here's the symbol that is actually used.
oh yeah, maybe we can ask professor. Maybe he's like he did it as a purpose or just abusing notation or maybe yeah.
But maybe in here, so if we're talking about just some sample questions to understand the terminology, so A relation A with respect to the exercise that we're given. So we have students in college, and A relation to A means do I consider of myself as my own friend? Is that how we should understand it? Or is there some? Yeah.
So we define the instead as this relation as the first hand component think B as a friend. So also even it is not a function, the order matters in the pair.
And for the classification, do we call this type reflexive? Is that this
No,
type?
I think it was reflexive, right?
Yeah, well, ARA is the reflexive term,
Wait,
right?
is it? I mean,
Everyone is friends with themselves.
Yeah. Here's the definition before for reflexive.
Oh yeah. So yeah. So this was reflect. This was symmetric and that was reflexive. Yeah. Okay, so maybe we can just think about this as a normal like situation. So if we define A think B as a friend for our relation, then so what do you mean by A relation? A means like A think of A as a friend, right?
Yeah, does A consider himself to be a friend?
And
well, it's more philosophical now than mathematical.
Yeah.
Yeah, exactly. And if A think, oh, this is a bit sad. If A think B as a friend, then B think A as a friend. I hope so, but like it's not always the case.
But then if it is the case, we then call it reflexive, right? That's
yeah. If it is the case, we call it reflexive.
no. Sorry, we call it symmetric.
Symmetric, yeah, symmetric. So like generally in our definition of relation here, we can say it is reflexive because I think at least every person can think him or like herself as a friend or whether like any kind of itself as a friend.
So I think it's also maybe important to note that in mathematics you don't have a way to figure out if the relation itself is correct. So it's just like you have the relation, but there is no clear distinction of choosing it, right? So such discussion depends on specific students and their specific thinking about themselves and others. But it's not part of the mathematics itself.
Yeah.
Mathematics only allows you to have the framework with which you can work to achieve those
And
results, but not
And also like we require objective,
yeah,
like
objectivity, I think, as well.
I think that's why we like really try to struct our set as a like from the logic, from like in like universally.
I think it also was in the definition of set. We said X is an element of a set means that we can clearly distinguish. Like there is a clear logic by how you can say whether it's an element or not an element of a set. Definitely. So there is no subjectivity in this case involved, right?
Okay, I think today we can read until here the definition of reflexive.
And maybe just the third example as well. So we have the if A so if A thinks B is a friend and B thinks C is a friend, does A think C is a friend? So is a friend of a friend considered your friend?
Yeah, it might be depends on the like cultural context.
Yeah, exactly. I mean, if it's social media, it can happen, but
So
maybe not
like
in real life.
maybe like and also it depends on the generation. Maybe like in our my parent generation in South Korea, like in this relation transitivity holds, but in my generation, it's not really, and maybe younger than me, they definitely not think of like yeah, like that. So there's transitivity and also
But I don't think many people are considering the relations like if these are my relations reflexive, symmetric, and trivial.
okay. Yeah, and symmetry, we already deal with this. And yeah, I think here we just introduce the like aspects about relations only consist what equivalence relation is because there is also like antisymmetric and like
So in other words,
tautology.
if those three properties are not satisfied, then the relation is not an equivalence relation. That's the idea, right?
Mhm. So and this is just Korean exact translation about equivalence relation and if R satisfies so equivalence relation should satisfy reflexive, symmetric, and transitive. So
And maybe just a small side question. So, are there any famous other types of relations? So, not an equivalence relation, but other types? Because I only have seen the equivalence relation as something studied,
so
but maybe some relation which satisfy some other set of properties, but
so
are also common
so
in
linear
studies.
order
Linear order
is also
relations.
relation. I'm not sure like it has like totality and antisymmetry
Mhm.
and transitivity.
I think so,
I'm
yeah.
not, I'm not sure, but so linear order. So from transitivity, we have like triangle inequality,
Mhm.
and yeah, antisymmetry makes the order, and totality makes sure that like
All
every
elements are covered.
yeah.
Mhm.
And also there, I heard that there are like not linear order, but kind of like maybe semi-order or maybe
Semi-order, yeah,
yeah,
that's
yeah.
right.
That is also kind of relation. So any kind of thing can be relation, but I think we really interested in equivalence relation because is it like useful in terms of mathematical like structure or like proceeding. Yeah. Anyway, so we have reflexive, symmetric, and transitive, then we call the relation as equivalence relations. So okay,
Yeah,
so
I think we can conclude till here today.
mhm.
That
Mhm.
will be all right.
Yeah, and
So far
like
in the definitions, there are not that much of a in detailed examples. It's just written like if x y is element of R, then y x is element of R. So we all only know the condition how they actually become transitive, symmetric, and reflexive.
mhm,
Maybe later we can encounter the examples.
mhm.
Yeah.
So I think this is it for today, and I want to shortly discuss like whether so we will take a break until due to our exam period, and we will start our like session again
So
from first.
roughly in August, yeah, in
Yeah,
August we can
like
start our
first
session.
Monday in August. I think I wrote the date. And I want to ask, should we proceed the same time
Maybe it will
or?
be clearer by maybe a couple of days before it. We can check and confirm the times for each other.
Mhm.
So maybe as you are the moderator, you can publish the time that you would
Mhm,
advise
mhm,
people to meet
mhm,
closer to the date, and then we
mhm,
can each say, depending on our situations, if we can,
mhm, mhm.
right?
So anyway, our first meeting will then held in the same time, and then in August we can discuss about like so we will start our like next semester at like October 15th.
Yeah, middle of October, I think,
Yeah,
is
yeah,
the start
middle
of the
of October.
semester.
So we have like
So in the meantime, will it be okay if we want to do like 2 sessions a week, if it's possible? Sometimes maybe.
sorry.
We didn't hear you. Sorry.
I mean, we can try to do 2 sessions per week also if you have time. I mean, after the exam
So
till
like
October.
like 2 times in a week, kind sort of like.
I mean, yeah, if it's possible. Of course, it's not necessary.
So
We
far, I
can
don't.
discuss
I,
it.
for me, I don't see any trouble. Generally, I think it should be possible.
Yeah, yeah. So I also want to do that, but yeah, yeah. So maybe we can
We'll
ask.
be able to know it better when we'll start again, I think.
Yeah, because like in semester break we can put more time, so it would be great for us
Mhm.
because during semester it is not
Yeah,
kind of
limited by the
restrictive.
study.
Yeah,
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 yeah. Mhm.
Yeah, it's understandable.
yeah.
Yeah, sure.
Yeah, okay. So this is it for today, and I hope you not. I hope you doing well inside of the humidity and of monsoon,
Yeah.
and yeah,
Yeah.
always best choice to start Monday morning. And yeah, any comments?
Not to the moment. Shall we stop recording for?
Oh yeah, yeah.
Yeah,
Okay.
yeah, the
It is.
recording should
It is.
stop.